Swayam Prabha. Digital India. Educated India.
Okay. Good morning. So, today we will cover actually three different topics. The first one is the ring opening of heterocycles initiated by lithiation, or you can say lithiation initiated ring opening. Normally, this is restricted to the 5-membered ring systems. And then we will also talk about this lithiations of I would say a pyridine nucleus, which is a representative nucleus for 6-membered heterocycles. And third item that would also, of course, the lithiation of non-aromatic heterocycles. So, these are the few topics we will cover. Then maybe towards the end we will have an example of the total synthesis, how the lithiation can be exercised to shorten the total synthesis. And prior to that, very quickly we talk about a little bit of the azulene. If you recall, last time we said that azulene can be made very easily from zinc salts. Zinc salts is nothing but a salt of a pyridine nucleus. Normally, many of us know how to make DNP, 2,4-DNP. How is it made in lab? You use DNP, but if you are asked to make DNP, how do you make it? Chloride. So, corresponding chloro compound. Just like Sanger's reagent. So, what you do, you treat this with pyridine, but this is such a nice and facile reaction. Pyridine displaces also this chlorine. So, eventually what you will get is a salt of pyridine, that means pyridine plus and this chlorine minus, and this compound is also very reactive. If you react with dimethylamine and then pyridine again. So, what is normally you would not expect any kind of reactions. At best you will expect reactions, the nitrogen lone pair attacking these 2 positions of the pyridine, because that is the most electron deficient position of the molecule. And eventually what you will get, actually then if you just sit down and do a little bit of the reaction mechanism, what you will find? You will find a molecule which is a ring opened molecule. That is the idea, a ring opened molecule. And so, you will have one side you will have a donor, that means free amine, other side you have iminium, that is acceptor, donor acceptor kind of molecule. And this sort of molecule is very useful actually in the preparation of dyes. Okay, you see there are a lot of references, and this sort of also known compounds are known as zinc salts. Okay. And Hafner, a German scientist, worked on this sort of molecule, and he reacted with cyclopentadiene in the presence of sodium methoxide. Sodium methoxide at high temperature around 125 degree centigrade, and then also unusually the reaction was carried out for 4 days. Maybe he was on leave, so 4 days, and the product you would not expect. It was a very nice clean synthesis. very nice clean synthesis, and the product was, so the product was what is this? Azulene, azulene. So, you see essentially you can say these two could be one step, and this is just one step, two step synthesis. If you go back to the original synthesis started from, anybody remembers? Good.
Naphthalene, then batch reduction followed by ozonolysis, aldol, and then dehydrogenation.
Maybe, yeah, look, sounds okay, but what the one I recall, it starts from cycloheptatriene, then 2 plus 2 cycloaddition, and forming a 4-member ring systems, then ring expansion and all those things. It takes a lot of time, a lot of steps also. So, this is just an example that the heterocycles are susceptible to undergo ring opening. Towards the again end of the course, we will have just a special topic of rearrangements and ring opening, etc. Okay. This was in connection with the ring opening lithiations in the 5-member ring system. Then what I said that we will also talk about tosmic, right. Tosmic is a very useful synthon in chemistry, and it is nothing but it is tosyl group, then CH2 and NC. So, isocyanate, tosyl methyl isocyanate, okay, which is equivalent to is carbon and nitrogen and carbon. So, if you are coming across a unit of carbon, nitrogen, carbon in a 5-member heterocycles, then one of the possibilities could be the use of tosyl isocyanate, this tosmic. And the first person that who popularized this is Van Leeuwen, is a Dutch chemist, and people often also call Van Leeuwen oxazole synthesis. Van Leeuwen oxazole is a very important molecule again in medicinal chemistry and these things. And what can be done if you elaborate this structure, it would look like sulfone, CH2, then isocyanate, and these, and tosyl means you have to have a methyl group of here, and the reaction conditions are very easy. Potassium carbonate, that is not expensive base, methanol, and probably heat, and the other reactant is benzaldehyde. So, that means reaction the starting materials are pretty cheap. What you get? You get a single product. And obviously this oxazole you get. Other things, the toxic acid, etc., comes out from the reaction. Okay. What is the mechanism? I think anybody can do it, right? So, mechanism wise, only thing you have to remember is reactions initiated by a carbon ion formations, not the lithiation though, it is a potassiation. That means the first a carbon ion is formed. So, sulfone and let us say tosyl, or I should not say tosyl, okay. These then okay, or you can say this minus, and it forms the anion up here. This aldehyde means you have double bond, right. This is phenyl. So, it goes there and goes to the carbon, and you have this. So, what you will find? I will find the sulfone part here, nitrogen is free now, carbon ion, and this oxygen and this. That is it. What next? So, that basically now if you look at, this is nothing but it is an heterocycle. So, that means heterocycles and it is a carbon ion. So, or you can say it is a potassium salt of the carbon ion, potassium salt of the heterocycle. Well, it can undergo exchange with this hydrogen up here. So, if you have an exchange, there are two other, all other possibilities. then you have a sulfone up here and carbon ion is formed, pH, oxygen and this. So, obviously, then you have a sulfone moiety which comes out as a leaving group. That means, sulfone has dual purposes. It can activate the alpha position as well as it behaves like a leaving group. So, you get this. So, that is not the problem at all. So, it is a very standard protocol now. Now, if you just change the other reactant, for example, if you I mean just I will quickly write this, if you have something like this acrylonitrile. So, what do you expect? Acrylonitrile means I mean acrylonitrile. So, what you will see just blindly you can write this acrylonitrile means this portion is cyanide, this is the benzaldehyde double bonded oxygen. So, it is now acrylonitrile. So, you have hydrogen and what else? Nothing, sorry. So, you will have it is a pyrrole, you will get a pyrrole synthesis. So, actually you can also say it can be used for the synthesis of pyrrole. Then if you let us say take with the phenyl diazonium salt, you will get the triazole. Triazole because tosmic gives 1 nitrogen and diazo compound gives 2 nitrogens, you get triazole, and that should be 1, since it is a diazo compound it has to be 1 and 2 and then 4 triazole. I will not write the structure. Okay. So, you can just work it out, that means it is a versatile one. This trick, that is the first one is the addition of the carbon ion to an electron deficient carbon and then cyclizations and forms the 5-member ring. All the 3 acceptors, benzaldehyde, acrylonitriles, or the even you can use ethyl acrylates for the synthesis of the corresponding compounds. Okay. So, it is a very useful one. There are other methods I am pretty and then how to make it quickly, I mean how to make it. This is a standard substance and commercially available, very cheap. Sodium toluene sulfonate. This is available in my lab, I can say. If you mix with formaldehyde and formamide, plain reagent formamide, then the formic acid is actually used as a solvent and water is standard protocol. So, what you will get? You will get sulfone now, mind it, this was a starting was sulfonic acid and now it becomes a sulfone. This CH2 comes from this formaldehyde and the rest part is basically comes from the NCHO comes from actually the formamide. So, what next? Then you have to know how to make isocyanates. How many methods do you know of till today for making isocyanates? Amine plus chloroform and sodium hydroxide. Carbonyl. Any other methods? Do you know?
Bromide and silver nitrate.
Okay, yes, bromide displacing that, but if just any that is what this is a formamide, but one of the dehydrating agents is required, that is all. POCl3 and triethylamine, there are many other reagents, Burgess reagent and all other reagents, then carbon tetrachloride, diphenylphosphine, there are plenty of methods, but this is most commonly used one. And so, what you get is the corresponding this one sulfone, CH and NC, no problem, without any problem. This is a very nice standard technique now. Okay. And but what happens if you instead of the tosmic take tosmic and then you take acetone, what is the difference? Acetone and the reagents are normally potassium tertiary butoxide and the solvent is DME, it is a polar solvent because potassium tertiary butoxide is being used. So, what do you expect? So that means actually the elimination would not take place. Elimination would not take place. That okay. So what you will see that sulfone okay is there. Then see the CH2 would react. You have the cyanide, and then acetone. So that would lead to CH3 and CH3, then oxygen minus. Okay. Then so what you will get? You will get again a 5-membered ring. 5-membered ring with a sulfone up here, nitrogen, double bonded carbon minus, and in this case oxygen and this, right. But previous case with the benzaldehyde you had a hydrogen up here which was exchangeable. There is no hydrogen at the moment. So, so what is expected now? So what is the expectation? This is anion can exchange with this hydrogen. So if you have anion exchange with this hydrogen, so sulfone, nitrogen, and this hydrogen up here, methyl, oxygen, and this. Okay. So again this is a 5-member heterocycle, and it has a propensity to undergo okay. So sulfone and this nitrogen and then double bond NH, and what you will have now, right. What next? Actually then one can see that you have an ion here, elimination will take place. So you will see now and then double bond, and it is sort of an isocyanide, sort of an iso.
For beta elimination, antiperipherality is required. So is it possible to attain that?
Let us say okay. So let us come to this first, and then okay. So far so good, I guess, right. I think we made a mistake somewhere, maybe. No, yes. You see, this one would be CH and this. Okay. There is other possibility also. You can actually postpone the loss of the sulfonate part towards the end. Any other mistake? Huh? Oh, I see. Oh, okay. Right. Single bond. Okay, fine. So then if you treat this with a base, the butoxide. So butoxide would deformulate, and eventually somewhat like that Wolff-Kishner reaction, it will form and a alpha carbanion, and which eventually in the presence of protic base what you will get? You will get the cyanide. There are other method also. I mean, you can just work out the other possible mechanism, but what is essentially see that it is a direct homologation process, direct, and there is no parallel. And it is a very unique homologation process. You can just increase the number of the carbon and remove the oxygen. All these things together can be done and to get to this compound. Okay. And this is a very general reaction. It is a very general reaction. And in fact, if you have even gigantic molecule, you can specifically homologate the corresponding keto groups. Then there are very similar compounds. For example, I will give you one more example where heterocycles have been used to functionalize molecules. For example, if you have a molecule of this kind, it is a ketone. Now, how would you introduce a carbon here at the alpha position, especially cyano group? I mean, obviously everybody would say, okay, you do the chlorination, right, chlorination and displace the chlorine with cyanide. Displace the chlorine or bromine by cyanide, yes, it looks okay, but most of the time the reactions do not really take place in the way we want. Okay. Alternatively, this can be converted into isoxazole. Isoxazole.
Sorry, first to generate the enolate and then
Enolate and then yes, mechanistically, electronically they look good, but they are not, but when you go to the lab, that is the disadvantage, you can say, advantage you can say, I mean, that is it's little problematic. I mean, when I say problematic means discovering a new organic reaction is important, that is perfectly all right. At the same time you have to develop it to make it usable. That means maybe at some point somewhere the reaction was discovered, but then eventually it did not turn out to be the best possible method. So that means people start forgetting things. The one those are useful. Okay. So this is another way of doing it, and this isoxazole. If you take isoxazole, and our interest is just to see what could be the possible reactions. Isoxazole, let us say 5-member heterocycle, right, and if you treat this with sodium methoxide, just a strong base, what do you expect? Normally we would expect that it is a methoxide, it will and oxazole means you have a carbon double bonded nitrogen, so it is a Schiff's base, but the Schiff's base analogy is only can be drawn for 6-member rings, pyridine and the corresponding isoquinoline, quinolines, etc., all these things, but not in the 5-member view, they are pi excessive. So, well, again, if you have too many nitrogens, then you can bring the analogy of the Schiff's base in 5-member heterocycles, but otherwise not. Okay. So what is the other possibility? Other possibility that this hydrogen is sufficiently acidic, so it picks up this hydrogen here, and as I said in the beginning, it would ring open and form the corresponding cyanide. Okay. And so obviously then what you will get? You will get the corresponding things done. So that means one thing you have to keep it in mind, that whenever you are thinking of these basic reactions in heterocyclic chemistry, especially with the 5-member ring, there is a propensity, there is a possibility of the ring opening, and okay, that's what you have to remember. That's it, and that is particularly true for oxazole and isoxazoles. Next item is this 6-member heterocycles, lithiations. Once again, lithiation is important, and all of us know the pyridine case, for example. So when I say talk about the 6-member, our reference is pyridine. Pyridine is electron deficient, and to carry out all these kinds of electrophilic substitution reactions are not that very easy. So you have to think about the alternative for functionalizations. We have been talking about the reactions. Now you have ignored some of these classical reactions, but in many cases you have to resort to the classical reactions like halogenation, sulfonations, etc. Okay. Beyond that, the lithiation is a very useful reaction, For example, and if you have a pyridine derivative with say let us say in the example I have been talking about, let us say you have a chlorine of here. How would you introduce a substituents? So when I say E, actually E stands for electrophile. So this is the problem. Now you cannot think about the routine electrophilic substitution reactions, and almost always routine electrophilic substitution is a mess. It gives mixture of products, sometimes it destroys the starting material, all these problems are there. So you have to be little specific, yield should be high and it should be regioselective. Okay. and in this case the problem was solved by a new kind of a base which is now known as fourth base, Okay. If you are interested, the reference is 2002 JOC page number 234. It is not, it's not a very new base though. What it is actually it's a combination of butyl lithium, means n-butyl lithium plus I mean there is an abbreviation called LIDMAE, lithium dimethyl amino ethoxide, lithium diamino, or you can okay, that means lithium oxygen, then there you have two groups and this. So, lithium diamino ethoxide. So, again what is the advantage? I mean there are all working hypotheses, but this combination actually forms a nice kind of a chelate, with nitrogen. The proposed model looks like this. It forms a chelate with all kinds of things here and there. So, chlorine up here, then lithium. I mean you can sit down and do little bit of homework and then write all kinds of possible structures. It says that there is a small chelate and the chelate is lithium chelate, that is coordinated to again nitrogen, which eventually activate the hydrogen at the 2 position, sorry 6 position, hydrogen at the 6 position, that is it. That means both the ligands and the lithiating agent is butyl lithium, and the ligand is that diamino tertiary butoxide, ethoxide, and all these things first forms the coordinations with here, and then that delivers this butyl lithium to the 6 positions, that is it. This is the working hypothesis, and this working hypothesis works well. And obviously then I mean this induces the lithiation here at the 6 positions, and so you can write this, and then you can also write something here, but eventually when you put this E plus, the substitution takes place at the 6 positions, and this methodology has been utilized for many things. For example, if you use dimethyl disulfide, so you can introduce SME up here. Okay. If you for example I mean okay, in this example let us say I do not have these other examples, maybe we will give you one more example. I think the exact example what we have. Let us begin with one more, that was the 2 chloropyridine. Now, if you use 3 chloropyridine for example, now there is a problem now. 3 chloropyridine and 4th base, right, first thing, and second thing that let us say you use carbon tetrabromide. So, what do you expect? So, we know 4th base undergoes coordinations at the nitrogen, it delivers the butyl lithium at the adjacent positions. It could be at the 2, it could be at the 6, right, 2 and 6, but in this case 2 and 6 are non-equivalent. So, just you have to make a guess which one. So, that means these are the 2 possible sites to chlorine, because there is that means if you in the back of your mind, if you remember, the acidity also is an important factor in the lithiations. So, it is likely to be on this side, and that is what happens, fine. So, that means the circled hydrogen would be deprotonated or lithiated. Then what next? What is the role of the carbon tetrabromide? Yes, Joe is right. So, it will be brominated. This is brominating agent. Okay. Let us say if you want to produce dichloro, for example. See, mind it, if you want to appreciate the merit of a method, you have to think about the alternatives. Is there any other simpler alternatives for this? If no, then this method is very good. Okay. So, likewise you use the fourth base and then you have to use an electrophilic chlorine, and all of us know what is the electrophilic chlorine, N-chlorosuccinamide. Even chlorine itself is okay. But then that the chemistry is actually synonymous with a word called compatibility, right. I mean, we can think of plus and minus, minus and plus and all these things, electron moving here and there, but eventually when it comes to the flask, there should be a compatibility between the two reagents. So, that is the okay. And so, like we have been talking about N-chlorosuccinamide, chlorine, iodinium chloride is iodine plus. Okay. So, like this, but they do not work. And alternatively, that is what also I thought, because last time we talked about that also did not work in this case, simply because there is an abstractable hydrogen. So, you have to have a molecule very similar to like Abhishek suggested, but it has to have, be free from having hydrogen, no, hexachloroethane. So, it is 2-hexachloroethane, that gives rise to this one. Okay. And so, if you are, for example, if you want to put groups at the 3 positions, for example, in case of pyridine, what is the normal practice? Normal practice, this is all of us know that this is actually the typical chlorination reactions at high temperature, that we know that, and then other method, this is very useful though. If you use butyl lithium, just plain butyl lithium, what do you expect? These are the things you have to be little practice basically. There are 2 possibilities, right? 2 or 3 different for 4 different possibilities. That is what you have to think. I mean, first you think about all the possibilities, then you cut down the possibilities. Okay, what are the possibilities? It can abstract the proton from this side, it can abstract the proton from this side, it can do the halogen exchange. Third is chichibabine. So, you have all possible. Now, you are mature person, you are senior person. So, you have to rank them, which one is most facile and which one is least facile. That is how you have to reject some of the possibilities. Then probably your assumption or the prediction should be somewhat close to the right answer. So, which one do I take? Halogen exchange, unless the acidity is very high, halogen exchange is the preferred pathway. Okay. So, what you get here, you get this lithium done, and then you can, but this is not very, again you mind see here, this is not a good one though, this is not a good reagent. Why? It is not very stable. If you recall, pyridine reacts with butyl lithium, phenyl lithium in the chichibabine fashion. So, they can undergo self kind of condensation reactions. So, you have to trap it. The convenient trapping agent is isopropyl borate. It is pretty easily available. Methyl borate also perfectly alright, but it is low boiling. But this is trimethylsilane is good, very good, but okay, there is a difference now. So, we will talk about all these things again in, I think, in next month. Okay. Because in next few classes we will talk about this cross coupling and other things. If you recall, again the most popular one is, most popular cross coupling reaction, if you recall, most in the fourth year we taught 3 different cross coupling reactions, rather 3 or 4. Okay, there are many more, but 3 or 4. But again you have to rank them. Most popular is right, Suzuki. Next popular, okay, I would say I will not take Heck, I will take Negishi on my basis, my judgment. Third one, Heck. Fourth one could be Sonagashira, and then are many other things. So now you can see which one should I put? Boron. That's what. So boron is very actually user friendly. You can store them, you can keep them, you can do any kind of reactions. If you open up a recent organic letter issue, what you will find, someone has done very simple reaction and he has published in Orglet. Who is that? Research scholars. This is a question to the research scholars. Someone from India has very recently used an organoboron and did this reaction, he got a paper out of it in Orglet letters. And a very young guy, just only 4 or 5 years senior to you. He recently joined Bombay IIT and he was also offered from our place. Right. So what did he do? He took a organoboron compound, treated with bismuth nitrate, he got a nitrobenzene. What I am trying to say, organoborons are very user friendly, non-toxic, can be produced in large quantity and can be removed any time. And let us for example, if you want to for example convert a phenolic moiety to corresponding benzenoic moiety to phenol, you can take organoboron, oxidize it with hydrogen peroxide, plain hydrogen peroxide, that will give you directly the phenolic OH. I mean then somebody else very recently, if you just go to the literature, there is a scientist called Gary Molander from Pennsylvania State University or somewhere from there. He did something like this. He took tetrafluoroborate, phenyl tetrafluoroborate and reacted with something like bromine or something, he got a bromo compound. So again a nice publication. So conclusion, the organoborons are very useful, very versatile, okay, very versatile, and that is the reason I have chosen this example. First of all, that means you can easily functionalize. Once you have a boron up here, you hydrolyze it. So what you will get? You will get the corresponding pyridyl boronic acid, but then there is a problem. It is unstable. So what you get? You get what is it? It is again a heterocyclic molecule. What is the molecule? 6 membered means what is the surname? 6 membered in boraxogen. So you will have pyridine up here, pyridine up here and pyridine up here. So unstable data. So that means you have then again it becomes so stable it does not react. So you have to open it up, and now you see the use of what is it? Pinacol. So you studied pinacol in the context of mechanism and all these things, but they are now in the organoboron chemistry. Pinacol is very useful, very useful, very useful. There is a dipinacoleto diboron, I don't know, diboron, do you know or not? That is very useful reagent, Yes, many cases. So and so that means what you will get? You will get nice organoboron. That means you can go on doing this thing, that thing. Okay. And now let us quick.
What is the main procedure for deprotection of for removal of boron?
Oh, hydrogen peroxide alkali. Very convenient way of doing it. Okay. So that means this is just an example of this, a few examples of this lithiations in this periodic chemistry. Now we will give you a very useful example. from the current literature. This is again oil paper and published last couple of years ago. It's a very it's about the synthesis, or rather I should say elaboration of pyridine nicotine in very few steps, just very few steps to a natural product, isoquinoline kind of natural product, where you can say benzyl isoquinoline. Normally the isoquinoline natural products are benzyl isoquinoline, and then you have this dioxolane bridge and okay. So, this was done in 5 steps. Done in 5 steps. What I will do, I will not give you the problem, I will give you the answer, just I will write the reactions, you have to predict first, then I will write the answer. Okay. This compound is known as macrostomine. It is a natural product, it is an alkaloid, and it has beneficial effect, and that means on cardiovascular functions. Cardiovascular means related to the heart. Okay. I mean it is not a drug though, but there is a drug called papaverine, many of you know. Papaverine is useful as a cardiovascular drug, it is in the market, it is a natural product, it is a benzyl isoquinoline natural product, okay, it is an alkaloid. But this is a nice illustration of these organolithiums and the chemistry part, and obvious choice was nicotine, simply because you see part of the molecule resembles very strongly with the nicotine. Now, so if we let us say begin with something like this, I think I will very briefly write 4 base, number 1, number 2 hexachloroethane. So, what is the product? What is the product? So, you have 1, 2, 3, 4, 5, 6. Now, you have to have a prediction. Well, at least I can safely write by now that it would not undergo ring cleavage, because it is not a 5-membered ring. The 5-membered ring is okay, ring cleavage, and then there is a see here there is a lesson you have to also learn. It is an aromatic nucleus and non-aromatic nucleus. The next lesson is actually lithiation of the non-aromatic nucleus. So, you have not talked about it. So, you can by negation you can discard, okay, this that means it will go to the aromatic nucleus, fine. And now, you have 2 and 6. In on previous occasion there was a chlorine. So, chlorine assisted, but in this case you have an electron donating. But again at the same time you have to think about there is a possibility of the coordinations here with the nitrogen, which is chelation. That means, if you have a lithium here 1, 2, 3, 4, 5. Okay. So, it's right. Then which one do you think we should go? Because if you recall, this 4th base works in fashion with through chelation, doubly, triply chelated things. So, if that is so, then they would prefer it would prefer to have a chelation towards the less exposed or rather sterically hindered side. So, obviously the lithiation would take place on this side, and hence the chlorination on the other side, okay, on this side. And repeat again, 4th base and then this hexachloroethane. So, what do we expect? Hexachloroethane. Now, what do we expect? Oh, sorry, I should not say it is just now, it is not the 4th base, sorry. This is now Now it is okay, it is not this 4th base, it is the benzylic hydrogen could be one of these regions, but because the nitrogen is there, it is a Schiff's base. So, it should actually lithiate either the 2 positions in the okay, in this case now it is 6 either this one or this one or this one, and I thought I would assume that this one, but our prediction fails. Actually I do not know how he predicted, how Professor Cummins from North Carolina State University, he actually found, I have to look at the literature, but eventually it was found that this 4th position relative to the nitrogen has been the position. The butyl lithium actually deprotonates that one. Okay. I mean then again butyl lithium, what do you expect? Huh?
In between 2 chlorine.
Okay, lithiation. Well, likely, then what? Benzene, yes. Actually that is what the benzene, and the benzene has been trapped with this dimethoxyfuran. So, what you will get and the benzene would be forming, there is a possibility either this on that, but again unless and until you know very closely, this benzene is formed on this side, and then so obviously the 6 member transitions 6 member thing would be there, like the furan part adds to this methoxy of here, and then the pyrrolidine part remains as it is, So, you have to aromatize it. So, how do you aromatize? If you look at the final structure, this should be essentially a sort of a benzene ring, right. Okay, this should be a benzene ring. Oh, sorry, this there is a methoxy up here, there is a methoxy up here too. Sorry, you correct the structure here. So, you have to deoxygenate. It is not an actually aromatization. Aromatization is normally you can say deoxygenative aromatization, and this has been done with magnesium and titanium trichloride. Titanium trichloride activates these carbon oxygen bonds, and magnesium is a reducing agent. So, you can on the other hand you can say magnesium reduces this titanium tetrachloride to corresponding titanium 0, and so what you will get, you will get an isoquinoline now. Isoquinoline is now 2 substituted isoquinoline, and then you have methoxys up here, and on this side you have these the pyrrolidine nucleus, and if you look at now what you have to do, you have to connect one benzyl group, that means with an oxalate bridge, dioxolane bridge. Okay. That means basically you have to connect 2 units, one is this one, that means this start positions, and in this case the start positions to be connected. This is where you have to know a lot about these cross coupling reactions. Okay. Cross coupling, when you say cross coupling reactions, you have to know the metals and the corresponding counterparts, and as well as you have to look at the hybridizations of the carbon and the reactivity of all these things. Okay. So, these are the 2 things you have to take care. And now let us, but already this on this part you have a fixed chlorine atom. So, the position is fixed. Now, you have to choose something here. So, chemistry wise, I mean although cross coupling has eased many syntheses, but at the same time it has complicated the chemistry part, because you have to know too many things, then choice is very difficult. You have to make a right choice. When too many things, the choice should be also. So, what can I do? So, what group would you take here? That is it, nothing else. You have an halogen here. So, any cross coupling reaction, we have to have a metal or metalloids, that is it, metal or metalloids. So, the first one we would think we go from the left, boron, then what do you think? Metal, tin, fine, that goes to Stille coupling, in between zinc. So, you have to lower down a little bit, zinc and zinc or aluminum, all these things, and there one more which is becoming very popular, and in the next Wednesday we will be talking about magnesium. Magnesium is now becoming very popular, very popular. There are quite a few persons who are engaged in and they are trying to develop the magnesium, because all of us know it is pretty cheap, easily, and Grignards can, or rather Grignards can be obtained very easily, and so magnesium. And in this case you have this magnesium chloride, that is it. So, once the choices are done, that means in this case it is chlorine, on the other side you have magnesium, then the problem is solved. So, but only then you have to have a right catalyst. And how do you choose the catalyst? If you do not know anything about the catalyst, just say palladium, right. So, palladium has become so popular these days. I think anything it does not work, okay, palladium. So, just like our potato, you know. If you do not have any vegetable, just put potato. Okay. So, but well, there is a cousin brother of palladium also. What is? Nickel. Good, nickel. So, nickel, I think nickel, yes, that is this. Then you do this. So, it is basically a very comprehensive example of these lithiations, benzene, all these things, aromatic chemistry kind of things, and which are really compatible with the heterocyclicals. And next example is I think very quickly we look at non-aromatic heterocycles. Non-aromatic heterocycles. There are not many examples, but our well, there are cases also sometimes unique, but I think I will just take one or two examples. This is a pyrrolidine case. If you have Bock protected pyrrolidine and then sec-butyl lithium, one can although one can see a direct lithiation adjacent to this nitrogen, and then you can do all kinds of things. Once you have a lithiation done, then you can do this homologation, and you see oxygen, and you can do 2 carbon homologation, and you can do all these things. Okay. Now, if you put zinc chloride, so this was an organic electrophile, now you have this electrophile, and what is this reaction known as? Bock. What do you expect? So, again if you look at Joule's book, they will say zincation, like magnesium, lithiation, this is zincation, that means you will have a zinc there. And often we talk about this sort of transformation as and in the name transmetallation. So, transmetallation moderates the reactivity of the organometallic lithiums are very violently reactive. So, if you just want to moderate the reactivity, you just do a transmetallation to a heavier metal, like you can do it, you can substitute lithium by magnesium also, or zinc, cadmium, all other things, you know. So, the zinc is obviously once you have a zinc here, then your options are now very clear, well defined. You can do this Negishi coupling. Okay. Then there are methods where one can just stereospecifically stereospecifically produce zinc here. That means, and this is Bock. Okay. There are methods. So, what you do first, do the lithiation first, and then you can put tin here, stereospecifically with tin. And normally these stereospecific lithiations are done by a ligand called spartein. I think many of you know, right? Spartein is nothing but a tricyclic alkaloid, tricyclic naturally occurring alkaloid. So, that means this lithiation can be extended to these things. I think I will maybe we will stop here, or I will give you one more very important example. In fact, this morning I tried to look at some of the examples, but unfortunately I could not get it. But maybe I think many of you know, I guess. Let us see, or rather how many of you know that is important here. This is a very unique reaction. This is unique reactions. It is an epoxide, so heterocycle, non-aromatic heterocycle. Now, if you react this with an amide here, just like LDA, diethyl amide. So, what do you expect? Let us say, what do you expect? Anybody knows? It is a very interesting reaction. Actually, that would tell you the essence of the what I have been talking about. I have been talking about what is the section is about, that lithiation of non-aromatics, non-aromatic heterocycles. So, this is an heterocycle. So, you can guess what it is. So, that lithiation normally if you have an organolithium and etc., epoxide opens up. If you have an acidic hydrogen that is protonated, then epoxide opens up, all kinds of possibilities here. But in this case, I think I will give you the answer, then what you will get? You will get here. What is this? It's a bicyclic compound. It's a bicyclic compound, and bicyclic compound with OH and trans hydrogen and hydrogen. I hope you will be able to come up with the answer. Okay, the paper I could find actually just few minutes before coming to the class is this one. It does not give, but I can suggest that I am probably quite correct. Normally the epoxides, if there is no other possibility, it would undergo lithiations here. If it is highly substituted, there no other possibilities are there, then epoxidation takes place adjacent to the, I mean you can quickly recall that vinyl ether undergoes lithiation here. Do you find any resemblance? Yes, there is a resemblance, because double bonds behaves like triple bonds, or other triple bond behaves like double bonds. Ethylene and cyclopropane, for example, they have close reactivity resemblance. Okay. So, what next? Then what you can see 1, 2, 3, 4, 5 and maybe intramolecular transfer, probably intramolecular exchange through acylation. Eventually you are like this is I am proposing, maybe somewhere I am sure, almost sure that it should be somewhere here, and the hydrogen now comes here and there is a lithiation. This is called, some of you have probably studied, called, there is a reaction called transannular cyclizations. This is again an example of transannular cyclization. Normally transannular cyclization involves a carbocation and a double bond elsewhere. Okay. This is just the anionic version of the carbocation, and of course 1, 2, 3, 4, 5. So, that is it. Okay. So, I think we will stop, but this is a very useful one, and there are a lot of work going on these sort of things, especially epoxide lithiations. Similarly, also one can think of aziridine also. Aziridine means all of us know aziridine, if it is properly activated like sulfone etc., you can do this also lithiations, well provided all other possibilities are cut down.